Okay, so let's go through these guys. We'll just do kind of a quick review of what we talked about yesterday. Donna, can I have you turn off? Donna, can I have you turn off that front set? Thank you. All right. So for calcium sulfide, all right, if we look at our solubility chart, we always said you look for the negatively charged thing. Okay, so in that case, that's sulfide. Okay, right here. And I want to move down until I find, oh, there's calcium. Is it in the soluble row or the not soluble row? Soluble. All right, so that stuff is soluble. All right, so we put an S beside that. Okay, sodium oxide. Okay. Oh yeah, right. I forgot I changed the solubility chart, and now that's not on there. Actually, no, we can still figure it out because we do have this column here that has sodium in it. Okay, and it says it's soluble with most things, but not with these weird things down here. Okay, so we can assume then that that is also soluble. All right. So that one will be soluble. Potassium hydroxide, that one will be on there. Okay, so hydroxide's here at the very end of the chart. There's potassium, so that stuff is soluble. Whoop. Okay, lead 2 chloride. All right, so chloride is right here. Okay, if we go down, it's soluble with most things, but not with lead 2 plus. All right, that's down in the not soluble row. Okay, so that one would be insoluble. All right, tin 4 fluoride. Okay, fluoride is right here, soluble with most things. And it would appear as though tin is included with most because I don't see SN listed down there in the not soluble row. All right, so that stuff would be soluble. Okay, copper 2 sulfide. All right, same idea. Sulfide's over here, soluble with these things. Copper is not listed there, so copper must be part of most. Okay, that is going to be insoluble. All right, then we've got iron 3 oxide. All right, so we look back in here, and oxygen's not on there, so that one, sorry, we won't be able to do, okay, because we don't have iron or oxygen on here, because I changed the solubility chart, because that one was better than the one I had before, but it doesn't have oxygen on it. Okay, potassium fluoride. Okay, so we'll look that one up. Fluoride has its own column, soluble with most things, and potassium's not in the insoluble row. Okay, so that would be soluble. Silver fluoride. Soluble with most things. And I don't see silver down in that insoluble row either. Okay, so that one would be soluble. Alright, cobalt 3 oxide. That one we won't be able to do because cobalt and oxygen are not on here, so we'll scribble that one out. Okay, beryllium nitrate. Alright, so nitrate is right here in that first row, soluble with most things, and obviously not with this. In fact, pretty much every nitrate compound is soluble. Alright, so we've got an S beside that one. And then lithium 3 nitride, and I don't think I have nitrogen on here either. So we'll have to scroll that one out. So, okay, can't do that one either. Alrighty, so is that still making sense for everybody? Right, it's not a terribly difficult thing to do. Again, the situation you're going to run into with this solubility thing would be, I give you a chemical reaction, okay, you predict the products, which we'll get to next week probably, okay, and then you have to tell me, are any of these products going to be a precipitate, which means they would be soluble or insoluble. Insoluble. Precipitates are solids, right? They come out of the reaction as a solid because they won't dissolve. All right, so that's kind of where we're headed with that. All right, for today, okay, we are going to be talking about writing chemical equations. So what we have to do is review how we know a chemical reaction has happened, okay, or a chemical change has happened. We have to go over what the signs of a chemical reaction are, look at the different kinds, and then we'll start looking at how to write them. And that's probably all we'll get to today, and then we'll have to pick this up next week because Thursday and Friday we're actually working on your first research project for this course. All right, how do I know if a chemical change has occurred? We talked a lot about physical properties and physical changes already. Chemical changes are different. How do I know a chemical change has happened? What are some signs? Phil? There could be a change in temperature, change in color, Change of state. Okay, a gas could be formed, a precipitate could be formed. That's a change of state as well. Yep, we got temperature already. Okay, what else? Right, if we see bubbles, okay, bubbles are evidence that a gas is forming, okay? Again, that's a change of state, but bubbles are always a good sign of a chemical change. Sometimes the bubbles smell, okay? If after you mix two things together, a smell that was not present before is now present, that is also a sign that a gas has formed and you are now smelling the gas, all right? And so, another sign, obviously, there to look for. Right? Usually when you get a precipitate formed, usually the precipitate also involves a color change, which we mentioned, I think was the first one. Okay? Color changes are always indications that a chemical change has occurred. Now, why are these signs of a chemical change? Why do they tell us that a chemical change has happened? It has to do with physical stuff. Okay, you're right. Chemical changes can't be reversed. I can't get back the starting materials. Okay? But if I have something that's a different color after the reaction, is that proof that I have new material or different material than I had before? Because the new materials have different physical properties than the reactant material. Right? That's why all those signs that really are just signs that new physical or new things have been produced because they have different physical properties are the signs of a chemical change. Okay? They tell us you now have different stuff on this side. All right? Now, we also have to go back to Dalton's atomic theory. When I say I make something new in a reaction, that's true to an extent. Okay? Do I still have the same elements that I started with? Yes, I do. They're just in different combinations. All right. Obviously, I can't have, let's say, sodium chloride and calcium hydroxide on reacting with each other, and then on the other side have silver and gold. Okay, that's alchemy. We know that that doesn't happen. Okay, in a reaction, all that's going to happen is the elements are going to be separated, joined, or rearranged. Okay, that's what Dalton said, and we know that that's still true, so it's something we have to remember as well. All right. Now, the types of chemical reactions, we're going to go over the basic 5. Okay, there's basically going to be 5 types that we'll talk about. Okay, understand how to identify each reaction type. There are certain, they all have kind of a unique setup or a unique pattern. Okay, makes them easy to identify. And then lastly, how to write chemical equations. All right. For this, do you need to be able to write chemical formulas and chemical names properly? Absolutely. If you can't do that at this point, okay, life is going to become far more difficult than you thought it already was. All right, because when you write a chemical reaction, you have to make sure that you obey the law of conservation of mass. Okay, you have to have the same amount of everything on both sides. And if you don't write a formula correctly, you'll never make that happen. All right, and it gets really confusing and frustrating for people. All right, so we talked about this already. In a chemical reaction, the final products are chemically different. Okay, that's the definition of a chemical reaction. The final products are different, chemically different. Okay, from the starting reactants, and those are 2 terms that we are going to want to be familiar with. Okay, reactants and products. So let's say I've got a reaction that looks like this. Whoop, that should be a capital C. All right, so in a reaction like that, I've got hydrogen chloride, hydrochloric acid, reacting with sodium hydroxide. So a really acidic thing reacting with a really basic thing. Okay? These are my reactants. Okay? They're the things that are reacting with each other. Right? The other side are the products. Okay, that's not in your notes, so you might just want to write that, add that in somewhere. Okay, so that you've got it. Okay, so you know what side I'm talking about. Because in a reaction or maybe a question in a lab analysis or something, it'll say, in the products, which of the products is soluble? Okay, well, if you don't remember which side is products, you're going to look at the wrong side. Okay, and then obviously you probably don't have a very good chance of getting the question right. Okay. All right, now, on the product side of this reaction, are my products chemically different than my reactants? Are they these are different chemicals, agreed? They're the same elements, but they're different compounds. They're different. They're rearranged, okay? They've been separated and rearranged on the other side, okay? Obviously, this is very, very acidic. This is very, very basic. This you put on food in large amounts, maybe, if you're like me, okay? And this is what? Water. I would say that that's chemically different from what I started with. Okay, an acid-base neutralization reaction definitely produces products that are very different from what you start with. In fact, every acid-base neutralization reaction produces water and a salt of some kind, so an ionic compound of some kind. All right, if you do the mixtures right, you should always end up with essentially a neutral solution at the end. All right, provided you mix equal parts together. Okay, everybody with me there? Making sense? Okay. All right, and then we said here evidence. We said color change, odor change, okay, state change, energy change. That means temperature. All right. Most reactions get warmer, but there are a few, okay, that get cooler. All right, 5 types of chemical reactions, and we've got to be able to identify these, okay, just by looking at them. In fact, by next week, you'll need to be able to identify them if you only see the first half of the reaction. Okay, and that's okay because each of the 5 starts out differently. Okay, you will be able to recognize the pattern for each one. It's quite easy. All right, so our first type is basically the simplest, a synthesis reaction. Okay, if you synthesize something, what are you doing? Yeah, making it. Okay, forming it, building it, whatever. You're synthesizing it. You're making it. Okay, so a synthesis reaction makes a single compound from usually 2 elements. There are rare occasions where a synthesis reaction might be a compound plus an element making a compound. Okay, but those are exceptionally rare, right? If I was asking you on a test, I would obviously not give you one that was like that. Okay, anytime I test you on, it's going to be element plus element gives compound. Okay. Now, at this point, a lot of people ask, what's the S and the G for? Okay, the S and the G, and sometimes you'll see an L, or sometimes you'll see an AQ. Those are the states of matter. And it's just out of habit that I put them on there. In Science 10, actually, you don't have to. Okay, but for right now, you see them there up there if you want to know what they are. Okay, it's telling me that magnesium solid is reacting with oxygen gas to produce magnesium oxide solid. All right. Essentially, this reaction is if you leave a strip of magnesium out in the air, it will oxidize, react with oxygen in the same way that iron and steel react with oxygen. They oxidize, okay, and forms magnesium oxide, which is a black powdery substance. All right. Everybody with me there? You're never going to be asked on a reaction to predict the states of matter on it. You won't have to worry about that. Chem 20, yes, but not Science 10. Okay. All right, so these are our 2 examples. We got, in this case, potassium reacting with bromine to produce potassium bromide. All right, now, these big numbers, okay? You'll also see big numbers and little numbers, okay, attached to these, okay, so that you know what they are. These big numbers are called coefficients. Okay, coefficients are numbers that you multiply by. So they are essentially telling me how much of that material there is. Okay, it could mean that there's literally, like this one, 2 atoms of potassium. Okay, it could mean also that there's 2 moles, which is another unit of measurement in chemistry that we'll talk about later, of this material. Okay, that would be a lot more than 2 atoms. All right, in this one, okay, what does this 2 mean? Nope. That they're bonded together. Okay, little numbers mean Okay, these things are attached. This is a molecule. All right, this 2 means there's 2 potassium atoms that are separate. This little 2 means there's 2 bromine atoms in a single molecule of bromine. All right. How do you know when to use one or the other? The answer is you're going to take out your periodic table right now, and we're going to identify which ones are which. Okay? Okay. I tried to get you guys the color one, but it didn't work out so well. But you can see that they are shaded a little bit on yours because I printed it in black and white. So here's what you need to know. Okay, the ones that are in yellow here, okay, are molecular elements. Okay, actually, all the ones that are colored are molecular elements. It means that when they are by themselves, they are a molecule, not single atoms. All right, so they actually, oxygen actually bonds with itself. Okay, that's why the gas we breathe in is O2. Okay, there's lots of elements out there that are like that, and they are all highlighted here. All right, so anything that's in yellow is a molecular element pair. So it bonds with itself once, and there's 2 of them. All right, so that would be nitrogen, N2, oxygen, O2, F2, Cl2, Br2, I2, and acetatide 2. Okay, and hydrogen also. Okay, bonds with itself. Very easy way to get a full shell of electrons for hydrogen, because the first shell can hold 2, and that's the best way to do it. Okay, so they're molecular elements. They form a covalent bond with each other, okay, and come as a pair. And then there are the 2 weird ones. Okay, there's phosphorus, which is a molecular element quadruplet. When phosphorus bonds to itself, it does so 4 times. Okay, so when phosphorus is an element, it is P4. When it's an element, okay, not when it's in a compound. It could be any number in a compound. But when it's by itself, it comes as a set of 4. And then there are the sulfur octuplets. Okay, sulfur bonds with itself so many times, it comes as a cluster of 8 atoms when it is by itself. Okay, in case you don't have highlighters, I'll send around the closest I have to those 3 colors. Okay, just pass them around. If someone doesn't have them, they can use those. Okay, you can highlight them on your table there. Okay, so back to this. Sorry, did everyone have those? Okay. All right, so in a synthesis reaction, 2 or more elements react to form a molecular compound. Now we know why bromine had a 2 here. Bromine is one of the molecular element pairs. Okay, it always bonds with itself. Now, after the reaction, I get 2 molecules of potassium bromide. Okay, so there's a bromine and a potassium, and a bromine and a potassium. Okay. Everybody with me there? All right, so synthesis reactions are pretty easy. 2 things go together to form 1 compound. 2 elements to form 1 compound. Now, the other thing we need to look at is, are we still obeying the law of conservation of matter, okay, or the law of conservation of mass, whichever way you say it. Okay, that means I have to have the same amount of matter on the reactants side as I have on the product side. In other words, the same number of atoms. All right, how many atoms of potassium did I have on this side? 2. How many do I have over here? Still 2, right? This 2 means multiply everything behind me, okay, by 2. So there's 2 potassium and there's 2 bromine. Okay, so it's kind of like that. What do they call that in math? Foil? Have you done that where you go inside the brackets? I'm not a math guy. Just seems like something I saw before you were born. Okay, all right. And for bromine, there's 2 on this side because it says there's 2 here. Okay, there's 2 over here. So yes, we've balanced that reaction correctly. That's what we call it, balancing the reaction. We probably won't look at that much today. Okay, but it's something that we will do. Okay, the exact opposite of a synthesis reaction is a simple decomposition reaction. All right, and by exact opposite I mean just that. A single compound breaks down into its constituent elements. All right, which basically means it just separates. Right? We said, Dalton said in his atomic theory they could be separated, joined, or rearranged. Well, now we've looked at joined and separated. All right, the rest of the stuff we look at will all be about rearranging. Okay, so in our first reaction here, this is how they produce rocket fuel. Okay, they do the electrolysis of water. They run a large electric current through water, and that separates it into hydrogen gas and oxygen gas. Okay, so we've got water as a liquid going into hydrogen gas and oxygen gas. All right, now, how many hydrogens are there on this side of the chemical reaction? 4. Okay, remember, the coefficient is 2, and it means multiply everything in this compound by 2. 2 times 2 is 4. How many oxygen are there? Stephen? 2. Okay? I mean, if we don't see a number beside oxygen, we assume that there is a 1 there. All right, 2 times 1 is 2. All right. On this side, are there still 4 hydrogen? Okay, and still 2 oxygen? Then we're good. All right, it's important to know how those coefficients work. All right, and in this example here, we've got 2 molecules of nitrogen triiodide, okay, and that is breaking down into a molecule of nitrogen and 3 molecules of iodine. Here's why we just went over on your periodic table which elements are pairs, quadruplets, and octuplets. When you get to the point where we'll be next week, where you're predicting the products of a reaction, if you have a reaction like this, you'll have to know by looking at your periodic table that you need to go N2 and not just N when you're predicting the products. Everyone follow me there? All right, so that's why we did that. Okay, so we get a molecule of nitrogen and we get 3 molecules of iodine. In the end, 2 times 3 is how many? 6. 3 times 2 is how many? 6, so that's balanced. 2 times 1 is 2, and this says that there's 2 nitrogens on that side, so we know that yes, we've obeyed the law of conservation of matter, okay, and we still have the same amount on this side. All right, so a simple decomposition reaction starts out with 1 compound and breaks down into 2 or more elements, okay, depending on how many elements were in the compound. Okay. Is it possible in a reaction like this that it could also break down into, let's say, an element and a compound? Is that possible? It is. Okay, it's rare, but it does happen. Sometimes a decomposition isn't complete. Okay, so we start out with a single compound. That's always true. Start out with a single compound and break down into its parts. Okay, usually those parts are its elements, but sometimes it's an element and then an ionic compound or something. All right, Aiden? Because iodine doesn't bond with itself 3 times, right? It's just a pair. And that just has to do with its configuration of electrons, right? If you notice, everything that we highlighted that was a pair, or just about everything, was in this column, right? They all have 1 space left in their outer shell of electrons, so it makes sense for them to bond with another one that has 1 spot, and then they'll have full shells, right? Okay. Next one. Oh, I had it right there. Okay, anyway, next one. Combustion reactions. Combustion means burn, okay? Set on fire, burn. It actually means truly react with oxygen, okay? You must have oxygen for combustion to occur. You probably did that experiment in like the 4th or 5th grade where you lit a candle and then put a glass over top of it, okay? And the candle eventually went out because there was no more oxygen in the glass, okay, or in the cup or jar or whatever it was you covered it with, okay? It used up all of the oxygen and the reaction stopped because the supply of one of the reactants was exhausted. Okay? When there's no more of that reactant, the reaction stops. Okay? So, the nice thing about combustion reactions is they're obvious. You will always have a hydrocarbon, okay? So a compound containing carbon and hydrogen. That's a hydrocarbon. Okay? And it'll always be reacting with oxygen. Okay? The other nice thing is the products, regardless of what hydrocarbon it starts with, are always carbon dioxide and water. Okay? Just it depends how much carbon dioxide and water. The bigger the hydrocarbon, the more carbon dioxide and water you get. Okay? So these are always the products of a combustion reaction. Okay? That's the good news about combustion reactions. There is unfortunately a tiny bit of bad news about combustion reactions. They do tend to be the most difficult to balance. All right, when we start talking about balancing, I'll show you that there are 2 rules, only 2, that you have to follow, okay, specific to combustion reactions. All right, now in this reaction here, we've got C3H8. Anybody know what that gas is called to most people? Anyone watch? That's an old show now. King of the Hill, Hank Hill. What did Hank Hill always sell? Propane and propane accessories. Okay? Yeah, that's propane. C3H8. It's the stuff you use in your barbecue if you have a propane barbecue. Okay? If you have a natural gas barbecue, it's slightly different. All right? C3H8. Okay? And it reacts with oxygen gas. Now, we've got to check and make sure we've still got the same amount of everything on both sides. Okay? How many carbon on this side? 3. Okay? How many over here? 3. All right, so the carbon's good. Okay? How many hydrogen here? 8. How many over here? 8. 4 times 2 is 8. Now it gets tricky. Okay? How many oxygen here? 10. Okay? But oxygen's in 2 places now. Is that okay? It is. I just have to add both compounds together. Okay? So 3 times 2 is 6 plus 4 more is 10. All right, that's not that tricky, is it? It's just something you got to realize, okay? Sometimes in a reaction, an element might appear in both products. And you have to be aware of that when you actually go back and balance the reaction. All right. And again, the big thing here is the bigger the hydrocarbon, the more carbon dioxide and water you get. So you could have one like this. C8H18 plus oxygen gas gives CO2 and water. Okay, now, this is the little balancing rule here, but when you have an odd number of carbons, you can start the reaction with nothing, essentially a 1. Okay, but when you have an even number of carbons, you have to start with the first even number, 2. Okay, what's 2 times 8? 16. All right, so I'm going to put a 16 over here. Now I have my carbons balanced. Everyone okay with that? Okay, and then I'm going to balance my hydrogens. Just makes sense to kind of do it in alphabetical order. Okay, 2 times 18 is 36. All right, so if I put an 18 there, that will give me 36. Agreed? Okay, and now I don't know how many oxygens are here because it doesn't tell me. But could I figure out how many are over here? Yes, I could. All right, so 16 times 2 is 32. Okay, plus 18 more is 50. All right, what times 2 will give me 50? 25. That's about as hard as balancing gets. Okay, you'll practice it. If you didn't get it there, don't worry. Okay. All right, so you can see the bigger the hydrocarbon, the more waste products, okay, we get. 16 carbon dioxide versus 3. All right. Now, this is propane. This is octane. Where do you use that? In your car. That is the active ingredient in gasoline. Okay, if you haven't filled up a car with gas yet, when you pull up to the pump, there's usually regular, mid-grade, and premium, and they have different numbers on them. Regular grade is usually 87 octane. Okay, mid-grade is usually about 89, and premium is usually 91. All right, it's simply like a parts per million or a number that says how much octane is in that fuel. Okay, the more octane that's in the fuel, the hotter it burns, and the more power it generates. Okay, now, I know what you're thinking. I should just put premium in all the time. There's 2 reasons why you shouldn't do that. Some cars are designed to only run on 87 octane fuel, and if you put more higher octane fuel in, your check engine light will come on, so don't do that. Okay? Some cars are designed to run only on premium, and if you put regular in, your check engine light will come on. Okay? So you actually have to look in your owner's manual. The computer in your car is set up to run in a certain temperature range. Okay? And if it starts sensing that it's getting more power, it's pushing the pistons harder, it's running hotter, okay, it'll turn the check engine light on before you cause damage. I don't know if it's parts per million or not, Philip. It's a number that basically talks about the concentration or amount of octane that is in the fuel. Yeah, I don't know if it's parts per million or for sure or not. Okay. All right. Everybody good with that? I would assume it's probably not. I don't know why I said parts per million. That's not very much. Okay. All right. So that's kind of how combustion reactions work. The big thing to remember there is you always produce carbon dioxide and water vapor, and that's why on a cold day, okay, you can see the exhaust coming out of everyone's car. On a hot day, you only see the exhaust coming out of cars that don't run well, okay, because they're putting out particulates and other things because they're not properly combusting the fuel. Okay, if proper combustion of fuel is going on, you basically won't see anything coming out the tailpipe on a normal warm day. But when it's 40 below, okay, you can see all the water vapor, because when it comes out, the vapor immediately condenses, okay, and turns into liquid water, and you see the little cloud. Or if it's really, really cold, you ever notice what happens to the back of cars when it gets really cold? Okay, they get like this layer of like frost forming on the back of them the longer you drive. If it's cold enough, that stuff will come out and immediately turn into a solid and freeze right onto your car. Okay, so weird things happen. Okay, single replacement. Now, the rest of these reactions that we're going to go over, we've already gone over 3. We're only going over 5. Okay? The last 2 are both replacement reactions. And they involve always ionic compounds. Okay? You will never see a molecular compound involved in any of these replacement reactions, single replacement or double replacement, only involve ionic compounds. Okay, and they are appropriately named. Replacement is exactly what goes on in these kinds of reactions. Okay, in a single replacement reaction, my reactants are always an element, could be a metal, could be a nonmetal, reacting with an ionic compound. All right, so it's always going to be an element plus an ionic compound. It's going to be a single replacement reaction. Okay, now what happens is, in this reaction, that single element will replace one of the elements in the ionic compound. Everyone with me so far? Okay. The element in the compound it replaces has to be the one that is like it. So in this case, I've got copper reacting with silver nitrate. What kind of an element is copper? It's a metal. Okay? So it has to replace the metal that's in the ionic compound. For this reason, the products have to be an element and an ionic compound. All right? And an ionic compound always has to have a metal and a non-metal, okay, or polyatomic ion in this case. So if you end up on the product side with 2 metals together and a non-metal by itself, have you paired them up correctly? No, you haven't, because you don't have an ionic compound now on the product side. Okay? The way that this is often shown is with dance partners. So you got this guy who's all by himself, okay, and this couple dancing. This guy decides she's pretty hot, so he's gonna, roll this guy and take off with his girl. Okay? He didn't roll the girl and take off with the guy. Okay? In chemistry, chemistry's old-fashioned. Okay? That's fine maybe in real life, but in chemistry is very old-fashioned. Okay? And you always have to have a metal and a non-metal end up together, okay, on the other side of the equation. Everyone all right with that? Okay? The other thing is you never see 2 metals bonded to each other. Okay? It just doesn't happen. Right? Chemically, metals won't react and bond to each other. All right, so in this one here, copper reacts with silver nitrate to produce silver and copper nitrate. All right, now, That would be a cool reaction because it makes something valuable. Agreed? Except that this stuff contains silver and is also very expensive. All right? You're not going to get ahead, loading up on pennies in silver nitrate. Just chucking pennies into a solution of silver nitrate. You're not going to get ahead there. Okay? But when this reaction does occur, okay, what you will see is a clear solution with copper in it, whether you put pennies or copper wire or whatever in there. Okay? And by the next day, your pennies will look silver and the solution will be blue. Okay? Why will the solution be blue? That's right. Okay, that was one of the physical properties from our lab, right? Copper-containing ionic compounds are always blue, even in solution. Okay, and so over the course of time, that solution turns blue. All right. Okay, does that one make sense? All right. This is probably the one you're going to see most often, actually. Single replacement and double replacement are the most common reactions. Peter. They switch places. That's exactly what they do. Yeah. All right, let's check and make sure we balanced this correctly. Okay, how many copper over here? 1. How many copper over here? 1. Okay, how many nitrate are there over here? 2. Okay, this is the tricky thing. Okay, with a polyatomic ion like nitrate, nitrate is NO3. Right? That's what one nitrate looks like, NO3. Right? And there are 2 of them on this side. Right? That's what this coefficient says. Okay? So there's 2 nitrates over here. How many nitrates are over here? 2. Okay? We got a 2 outside the bracket. It means that there's 2 of them over there. Okay? That's where people will often make mistakes when they're balancing, is they'll confuse this number as applying to the whole thing. Nitrate is made up of 1 nitrogen and 3 oxygens. That's 1 nitrate ion. All right? Could you balance this like 1 atom at a time too? Could I just go, all right, there's 6 oxygens here, and there's 6 oxygens over here, and there's 2 nitrogens and 2 nitrogens. Okay, yeah, that's balanced. Could I do it that way too? You can. It takes longer though. Okay, if you're going element by element, it takes quite a bit longer. All right, last one. Double replacement reactions. Okay. In a double replacement reaction, you always start out with 2 ionic compounds. Always. All right. That's how you can tell the difference between a single replacement and a double replacement. Sorry, something slipped my mind. Got to go back to the last slide. Sorry, something slipped my mind here. Okay. In this reaction, I had a metal as the lone element. Okay. What if I had this reaction instead? Okay, could that occur? Okay, who's nitrogen going to switch with? Right, nitrogen is going to switch with the oxygen. Remember, I have to produce an ionic compound on this side. Right? I can't produce a molecular compound. If I swap nitrogen and iron, okay, then I've got nitrogen and oxygen together and iron by itself. That's a molecular compound. That's not happening here. Okay, so I would have Fe. This was Fe2, so this is going to be Fe3 and 2 plus O2. How did I know to put the 2 on the O? Right, it's one of the ones we highlighted. Okay, that's the only reason I know that. Okay, I don't just go randomly putting numbers on things. Okay, right, and I didn't just randomly put numbers on this. I swapped and dropped in my head. Okay, 3 and 2 on that one. All right, so now I've made an ionic compound and an element. Okay, now I want to go back and balance. I got 2 nitrogens over here, and I got 2 nitrogens over there. So that's okay. All right, how many iron over here? 3. How many here? 1. Now what happens if I put a 3 here? How many oxygen does that give me? 3. That's not very good because I have 2 on the other side. And there's no way for me to make that odd-even problem work. If ever I run into this odd-even problem, okay, the best way to solve that is to put a 2 at the front. Because by doubling an odd number, you'll get an even number. Okay. 2 times 2 is how many? 4. All right. What do I need to put in front of this compound to make 4? 2. Okay. So 2 times 3 is 6. How many oxygens does that give me? 6. What needs to go here? 3. All right. Okay. A little bit tricky, but that's kind of where we're headed with the balancing. Okay, back to double replacement. Okay, we start out with 2 ionic compounds, and we produce 2 different ionic compounds. Right? So essentially, all we have to do in this kind of reaction is switch the metals. All right? So when I'm figuring out who ends up with who, I just take sodium and put it here, and take calcium and put it there, and I've got my new compounds for the other side. Okay? They're replacing each other. Okay? And again, I've got to produce 2 ionic compounds. I can't produce 2 nonmetals together and 2 metals together. All right? That'll just look weird. Right, but I've balanced it. I've got 2 sodium over here, right? And I have 2 over here. Oh, you mean, sorry, if I was having to predict the products. Well, then I know who has to go together. That's why I'm saying I swap the metals. So let's do one like that, Philip. Okay, just to kind of put your mind at ease here. Let's look at. Okay, so I've got that. I've got magnesium nitrate reacting with sodium fluoride. It's a double replacement reaction because these are both ionic compounds. All I want to do to predict my new compounds is switch the metals. Right? That means magnesium ends up with fluorine. Okay, so I'm just going to write MgF for now. Okay, and sodium ends up with nitrate. Right? Now I'm going to check them for swaps and drops. I know who they're supposed to go with. Now I'm going to swap and drop them, and that'll make sure I get the right numbers. Okay? This is -1, this is +2, so MgF2, +1, -1, so that compound is fine the way it's written. Now I go back and look at the reaction as a whole. On this side, there's 2 nitrates. How many are there over here? 1. So I put a 2 here. Okay? That gives me 2 sodiums. I'm going to go back over here and make 2 sodiums. Okay? That 2 gives me how many fluorine? 2. Oh, well, that works out. Always a good sign when the last thing you have to balance is already balanced when you get done. Okay? Always means you did it right then. Okay? Does that sort of make sense? Okay? Notice, I don't, to balance, I don't put a 2 here, do I? Okay, to balance the whole reaction, I can only put in coefficients. When I'm swapping and dropping, I can put in the little numbers. Okay. All right, so big thing here is, again, just swap the metals and make sure you've got 2 ionic compounds on both sides, and that those ionic compounds are obviously different. Okay, if you write the same ionic compounds on the product side, that means nothing happened. All right. Okay, and here's one of those reactions I was telling you about where you mix 2 clear liquids together, okay, and you get a bright yellow precipitate. Yeah, it's one of the ones that you'll see in your chemical reactions lab next week. Questions on double replacement? Okay. When we communicate a chemical reaction, and this is what we've been doing on every one of the examples, okay, we've been making sure that there's the same number of everything on both sides. We've been balancing the chemical reaction, okay, making sure we obey the law of conservation of matter. All right, so in this equation, there are 3 nitrogen atoms on each side. There's 3 here, and there's 2 plus 1 more is 3. Okay, there are 7 oxygen atoms on each side. 3 times 2 is 6, plus 1 is 7. Okay, 2 times 3 is 6, plus 1 is 7. Okay, and there are 2 hydrogen atoms on each side, 2 and 2. All right, so that equation is balanced. All right, and it is very important that when we communicate a chemical reaction, we communicate it in that way. Okay. Right, so this is probably, because it's in italics, that's something you should know. Okay, in a balanced chemical equation, the total number of each kind of atom or ion, okay, is equal to the same, or is equal to the number of that ion in the product side. Okay, and when we're balancing, okay, that's when we use coefficients. Okay, remember we always balance with the big numbers, not by adding little numbers, okay, to compounds. Because if we add little numbers to compounds, we've probably messed up the swap and drop that somebody went to a great deal of trouble to make right. Okay, if I change the numbers, then I'm messing that up. Or if it's a molecular compound and I change the numbers, then it no longer fits with the written form, okay, that might have been in that reaction to start with. Okay, here's what I want you to do. I want you to do a few things on each one of these. I want you to identify the type of reaction that is occurring. Okay, so do all of those first. Just identify the type for all of them first. Okay, then write it out in words underneath. Okay, so essentially you're just naming. All right, so we'll do the first one together here. Okay, I've got, in the first reaction here, I've got an element reacting with an element, and it's forming a single compound. Which reaction type is that? That's a synthesis reaction. Okay, so simply write synthesis, or syn. Okay, now I want to write it out in words. What's this stuff? Nitrogen. Okay, so a lot of people look at that too and they want to go, it's dinitrogen. No, it's not. That's how nitrogen is as an element. Remember, it's one of the special ones. Okay, so this stuff is nitrogen. Okay, and it's reacting with hydrogen. And I can just write plus. You don't have to write reacts with, or is added to, or poured onto, or whatever. Okay, to form this stuff, which is nitrogen trihydride, also known as ammonia. This is the stuff you smell when you use glass cleaner. Okay, if you ever used sprayed Windex, that's the smell of ammonia. All right, then we balance. Okay, when you're balancing, the best place to start is with the thing present in the largest number, unless that thing is oxygen. Oxygen is the biggest pest when it comes to balancing reactions. Always do oxygen last, okay? Because if you try and do it first, you're going to be erasing everything and starting over again. All right, it's just a real pest when it comes to that. All right, so what's present in the largest number? Hydrogen is. Okay, there's 3 on this side, and there's 2 over here. What's the lowest common multiple of 2 and 3? 6. All right, so I'm going to make sure I get 6, okay, of each of those. So what do I have to multiply 3 by to get 6? 2. All right, so I'll put a 2 here. What do I have to multiply 2 by to get 6? 3. All right, now my hydrogens are balanced. How many nitrogen over here? 2. Ah, see, always a good sign. Okay, now nitrogen's already balanced. Nope, when we write a coefficient like we did there, the convention is that that applies to the whole compound. Yeah. All right, so that's what you can do. I would say just do the first 2 parts for now, the identifying and the writing out in words, and then come back and do the balancing for all of them after. Okay, because that's something we haven't worked on a whole lot yet. Okay, I know you can do the naming, that's no problem, and the reaction type stuff is what we learned today. Okay, let's have a look at a few of these here, guys. Seen the second one before? Yeah, because it was the example for what kind of reaction? Single replacement. Okay, so this is a single replacement SR reaction. Okay, written out in words, it's copper. Okay, plus silver nitrate. Okay, gives us silver plus copper 2 nitrate. Okay, how come I didn't have to write copper 2 on the other side? by itself. Okay, it's an element. Elements don't have a charge. Okay, so if you see one of those multivalent metals by itself, you do not have to write a Roman numeral beside it because it doesn't have a charge yet. Okay. All right, then I got a balance. What's present in the largest number? Nitrate. Okay, it's the only thing with a small number beside it. So there's 2 nitrates over there. So what needs to go here? 2. Okay, that gives me how many silver? 2. And now it should be balanced because there's 1 copper and 1 copper. Okay, so it's good. Okay, for our second one here, okay, we've got what kind of reaction going on? I've got a hydrocarbon and oxygen giving me water and carbon dioxide. Combustion reaction. Okay, so it's a combustion reaction. This is carbon tetrahydride. If you ever get one of these that's beyond the prefixes I've taught you, you can just write fuel. Okay, because that's what it is. It's fuel. All right, carbon tetrahydride or methane, okay, plus oxygen. Okay, it gives water and carbon dioxide. Okay, now I go back here for balancing. There's a 1 carbon here, and there's 1 over there, so that's good. There's 4 hydrogens here, and there are 2 over here. So what number needs to go in front of water? 2. Okay, that gives me 2 oxygens, plus 2 more is 4. So a 2 there will balance off the oxygens. Notice again, I did oxygen last. Okay, you always want to do oxygen last when oxygen is present, especially in a combustion reaction. All right. This one was also the example for which type of reaction? Simple decomposition, right? So I usually just write SD for that one. Okay, simple decomposition of water into hydrogen and oxygen. Okay, and then I got to balance it. Right now, it looks like the hydrogens are balanced, but the oxygens are not. Okay, there's 2 on this side, there's 1 over here, so a 2 there will make my oxygens work, but then it puts my hydrogen out of balance. Now I have 4 on this side and 2 over here. Now I have 4 on both sides. Okay. How many people are past that point? Okay, I'll give you a couple more minutes to get caught up with me. Hopefully we'll get them done before class is over here. Okay, so I've got, in this next one here, I've got a element reacting with an ionic compound to produce a new element and a new ionic compound. That would be single replacements. Okay, written out in words, that's chlorine plus sodium iodide gives iodine plus sodium chloride. Okay, and again, remember, we don't put diiodide or dichlorine or anything on these when they're elements. Okay, we name them as their element name sounds. Okay, and then we got to balance 2 chlorines over here, but only 1 over there. So I put a 2 there to fix that. That gives me 2 sodiums. So I put a 2 here to balance my sodiums, and that makes my iodines balance. Okay, so we're sure that that one's good. Okay, second last one. I've got calcium chloride, which is an ionic compound, reacting with sodium carbonate, which is an ionic compound. What kind of reaction starts with 2 ionic compounds? Quinn? What kind of reaction starts with 2 ionic compounds? Not single replacement, a double replacement, right? So, in a double replacement reaction, okay, so DR, okay, we would write out the names, which will take me forever, and the bell will go before I get it done. Calcium chloride plus sodium carbonate gives calcium carbonate plus sodium chloride. Okay, to balance, again, find the thing present in the largest number. That's sodium. There's 2 over here. So I put a 2 here. That gives me 2 chlorines. And there are 2 over here. And everything else is a 1. There's 1 carbonate and 1 carbonate. 1 calcium, 1 calcium. Okay? Tomorrow, we will be starting your first research project. Start thinking about a toxic chemical you might want to find out more about.